Look at this network grid. In a high-traffic environment, thousands of users are reading and writing data at the exact same time. Now, introduce a sudden server crash or a dropped connection into that environment. If a software developer had to write manual code to handle every possible intersection of concurrent user actions and random hardware failures, they would never finish. It is a practically impossible task. This is the problem database transactions were designed to solve. They provide a specific set of safety guarantees that define how a system behaves when those network errors and race conditions occur, and how much isolation it provides between different users. If those guarantees are missing, a single interrupted update can leave a database with half-written records. At scale, these small, unhandled failures accumulate until the application can no longer trust its own contradictory information. The core mechanism at work here is the transaction. Think of it as a logical grouping of reads and writes that the database treats as a single unit. It must entirely succeed or completely fail. This diagram illustrates a multi-step data entry process. Notice what happens when it hits an error on step 3. It snaps back to a blank state. This is the A in ACID, Atomicity. It is often confused with indivisibility, but it actually means safe abortability. If a process fails halfway, the database cleanly reverts all partial changes. By combining atomicity with durability, the guarantee that committed data is safely written to disk, developers can program as if the world is safe and sequential. They offload the terrifying reality of failures to the database engine. This brings us to the I in ACID, isolation. To understand what happens when isolation fails, look at this standard e-commerce checkout screen. Imagine user A is halfway through purchasing the last item. User B queries the inventory and sees uncommitted data. A millisecond later, user A's connection crashes and their transaction aborts. User B just read data that technically never existed. We call this a dirty read. The industry standard fix for this is called read-committed isolation. It uses basic locks on the data rows to ensure active transactions are hidden. Users only see finalized, committed data. But read-committed is a weak shield. It prevents reading ghost data, but as traffic scales, it fails against deeper temporal logic bugs. Consider a new scenario. Alice's app loads her 2 accounts during an active transfer. Account A loads at $500. The transfer completes behind the scenes. Then account B loads, showing $600. Her $1,100 total is read skew. Databases solve read skew using snapshot isolation. When Alice starts her query, the database grants her a frozen, consistent view of the past, completely insulated from any background updates happening in the present. Here's how it works. This 3D stack represents multi-version concurrency control, or MVCC. Instead of overwriting data, the database keeps time-stamped copies. A reader accesses an older layer at the bottom, while a writer simultaneously stamps a bright new layer at the top without colliding. MVCC tricks applications into thinking the database is frozen in time just for them. It allows readers and writers to operate independently, maintaining massive throughput. But even snapshot isolation has a blind spot. Look at this clinical dashboard for a hospital on-call scheduling app. Business rules dictate at least one doctor remains on duty. Right now, Alice and Bob both have bright green on-call status indicators. Both doctors check the app at the exact same millisecond. Alice sees Bob is on call, and Bob sees Alice is on call. Thinking the hospital is covered, they both log off. The hospital is left with 0 doctors. This is the write skew bug. Snapshot isolation allows this to happen because the transactions technically updated different rows. Alice updated her status, and Bob updated his. Their writes didn't conflict, but they were based on a shared, outdated read. To prevent write skew, we need an isolation level called serializability. Whether through 2-phase locking or modern optimistic checks, it forces the database to act as if concurrent users are waiting in a rigid, single file line. If you want to prevent write skew, you have to sacrifice parallel processing speed. Absolute data correctness requires a heavy toll on performance. We've covered A, I, and D. That leaves the C in ACID, consistency. It is widely misunderstood, and many engineers argue it doesn't belong in the acronym at all. The database itself cannot inherently know your business logic. It doesn't know that account balances cannot be negative, or that a hospital requires 1 doctor on call. It cannot enforce rules it doesn't understand. Consistency is strictly an application property. The database merely provides the tools. atomicity, isolation, and durability, so developers have a stable foundation to keep their own rules intact. This staircase chart summarizes your isolation choices. At the bottom, you have read committed for basic speed. The middle step is snapshot isolation, using MVCC to prevent read skew. At the top, you have serializable isolation, trading performance for perfect correctness against complex logic. Transactions safely group operations together, but picking an isolation level forces a deliberate choice. You must balance system speed against data integrity. Understanding these trade-offs is the only way to build data-intensive applications that survive the real world, rather than silently collapsing under their own weight.